have a cocktail together, right?
Ladies and gentlemen, our program will now begin. Please welcome the CEO of Churchill Club, Karen Tucker.
Thank you so very much. Hello. It's a pleasure to be here with you tonight. Really appreciate you coming out and joining our discussion called The Renaissance of Silicon, Part 2, Startups. The origin of this event was a trend prediction that Navin Chaddha from Mayfield made on our stage last May. He said that the renaissance of silicon will create industry giants. This trend was quickly voted to the top by our audience. With the end of Moore's Law, Navin explained, new semiconductors are required for a cloud-native, data-dominated, AI-powered IoT world. The rise of these new players will put silicon back into Silicon Valley. Last July, we held part 1 of this discussion with the CEOs of Micron, Xilinx, and ARM. And that discussion was led by Tammy Kiley of Goldman Sachs. And this one tonight, part 2, will look at the entrepreneurial side of the story. And here to weigh in are Navin Chaddha, John Hennessy, Rodrigo Liang, Pradeep, Sindhu, and Diane, Bryant. Welcome, all of you. We'll hear much more about our speakers and from them quite shortly. But first, some thanks are in order. We definitely owe a big debt of gratitude to Navin and Kamini and Kelsey from Mayfield, who enabled this program to begin with. Thank you. Big thanks also to DLA Piper for their support of the program. We appreciate that very, very much. I'm guessing that some of our new guests in the audience might appreciate a few words about Churchill Club. Next year will be our 35th as an independent, nonprofit thought leadership forum here in the region. Our mission is to strengthen innovation, economic growth, and social good. We try to, with the topic, the theme-centric programs that we produce, we shoot for what's new, next, not widely known. We try to advance the conversation rather than repeating what's already widely out there. We always ask our speakers not to pitch or promote, of course, and we don't really have a problem with that here, which we appreciate very much. We convene about 24 programs every year, and we consider our audience to be quite exclusively the active and dynamic people who are pushing industry forward in various dimensions. In all kinds of different segments. Our very first speaker, by the way, back in 1985 was Bob Noyce of Intel. The hashtag for tonight is Churchill Club, and there are a lot of other relevant Twitter codes in your programs. It's time now to welcome a special someone to the stage who has been practicing in DLA Piper's Technology and Sourcing Group for over 25 years, and that someone is Victoria Lee, partner and global co-chair of the technology sector at DLA Piper, and she will introduce our panel. I would like to also point out that the full bios are in the printed program tonight. So let's welcome Vicki.
I really only have a bit part here tonight. Thank you, everyone. Thank you, Karen. It's always dismaying to me to have to put on my glasses here. Welcome to what we hope is going to be a really interesting discussion. I'm very excited to be here with you tonight. The Churchill Club's mission of bringing together driven professionals and leaders to discuss what's new, what's next, and what we don't know in a mutual quest for new opportunities and insights is something that we greatly appreciate at DLA Piper. Like the Churchill Club, DLA Piper has been hard at work, and we have deep roots here in Silicon Valley. By the way, I didn't know Silicon never left Silicon Valley. Since the 1960s, we're very proud to have assisted many of the world's leading technology companies in a full range of areas. Our entrepreneurial and collaborative culture fuels and supports growth and vision for startups and multinational corporations around the world. We know that new semiconductor technology is needed to fuel and enable the many exciting innovations in the AI, IoT, 5G, data-centric world that we're all living in. There are areas with incredible promise to fuel social innovation and economic growth. Tonight, we'll focus on the startup side of the semiconductor story and what lies ahead. We have a magnificent group of speakers to lend their perspectives, and it's truly my privilege and honor to introduce them. Navin Chaddha, Managing Director of Mayfield. Knight-Hennessy, President Emeritus, Stanford. Shriram Family Director and Stanford Knight-Hennessy Scholar and the Chairman of Alphabet. Rodrigo, and I apologize in advance if I mispronounce any of the names. Rodrigo Liang, co-founder and CEO of Samba Nova Systems. Pradeep Sindhu, co-founder and CEO of Fungible and the founder of Juniper Networks. And finally, Diane Bryant, former senior executive at Intel and Google Cloud, and twice named among Fortune 50's most powerful women in business, to both guide and hopefully also participate in the conversation. Again, it's my pleasure. Please welcome our panelists and our moderator.
Everybody know where you're sitting? Ooh. These aren't very sturdy if we fall off.
Are you trying to fall?
They're not very sturdy.
Oh, really? Maybe we can.
They're mini stools.
Mini stools. Okay. Okay, so we're going to get started here. Thanks to all of you for coming. Hopefully this will be lots and lots of fun for everyone. So the overarching premise of this discussion is that Moore's Law is dead. So you can, having been at Intel for 32 years, I know Moore's Law quite well. So, but so seriously, so you can agree that Moore's Law is dead, and then you need to ask yourself if it's even relevant. Or you can say that Moore's Law is not dead, it's just a bit sluggish. So to go back to what Moore's Law actually is, because it gets quoted in so many bizarre ways as to what Moore's Law is. So Gordon Moore, and he's told me this directly one-on-one, so, and he's actually corrected it a few times when I get it wrong. So Moore's Law, as stated in 1965 by Gordon Moore, is that the number of transistors per square inch of integrated circuits doubles about every year. And when he said to me, he also said very emphatically, it is not a law. There is absolutely nothing inevitable about it. And so that frustrates him that it was called a law. And then he says it was simply an economic observation, that the transistors will continue to shrink to the extent that silicon becomes free. And as Andy Grove used to tell us, calculations at some point will be free. So, I have to add, at Gordon Moore's 50th anniversary for Moore's Law, so 4 years ago, he was interviewed, and the question to him was, does it frustrate you that there's so much industry banter about Moore's Law being dead? And he looked at him in his little humble way, and he said, I'm surprised it lasts this long. So, the questions now to the gang here are, either you believe it's dead, and then, as an industry, we need to figure out what the problem and the solution is going to be, because we've got a big change here. Or you can declare that it's not dead, and then you have to ask yourself, is it even worth the investments that we're making in advancing silicon technology? You know, if silicon is free and all the value is above the stack, are we going to get an ROI on it? So someone can lead, anyone can lead, and you got to take a stand if you believe it's dead or you just believe it's sluggish, and then you got to answer what we're going to do about it. Who's going first?
Well, I think, as you said, Diane, it was an ambition, a goal. And I think to say Moore's, but there was no Moore's Law. It was something to shoot for. It's definitely slowing down. To say it's dead is premature. But I think more importantly, the failure of Dennard scaling, and the reason the press doesn't talk about it is they don't understand it. It's more complicated. Now we're talking about energy and something and power, and it's more complicated. But the failure of Dennard scaling, which is much more acute, began earlier and has really reshaped how we think about processors. Who out here who's been in the industry for a while would have guessed that microprocessors would slow their clock down or even turn off cores to prevent burning up? If you told me that 30 years ago, wait, you're out of your mind, it's never going to happen. But it has happened. And so that's really represents a a key problem, and meaning we have to focus much more on efficiency because we can't take for granted what Dennard scaling and Moore's law was delivering for 50 or 60 years. So.
Yep.
I
Navin?
agree.
So-
I agree with what John is saying, right? Like clearly, Moore's law is plateauing and slowing, but I'll take the second part of the question. Does it make sense to continue on the silicon investments, right? So as we know, right, like performance and power are really, really important. There's just tremendous growth in end users, whether it's on mobile, whether it's on the internet, and we are space constrained, whether in data centers or on our devices. So both performance and power are extremely, extremely important. And as a result, either we keep going on the evolutionary path of essentially just faster CPUs and everything happens in software, or we take a step back and we look at, hey, if we look at this as a systems problem, what could we do differently? And my belief is the world is moving from convergence in semiconductors to specialization, where some of the stuff that benefits from Moore's law, like CPUs, stay, but there'll be other things from a systems perspective around it. We already know GPUs exist there. From NVIDIA, we know network processing units exist. Similarly, there'll be like AI/ML chipsets. There'll be what Pradeep will talk about.
But are you saying they won't benefit from Moore's, or they don't need the benefits of Moore's law? They need that continuous progression of power and performance as well.
They need both, right? So essentially say, instead of doubling processing every 18 to 24 months, even if you go 20 to 30%.
So you're okay with it just slowing. Sluggish is better than dead.
Yeah.
Okay, and Pradeep?
All right, so I agree with what's been said so far, but there's a whole bunch of stuff to add.
Yep.
First of all, as it was observed, there is no law like Moore's law, but there is another law, which is the economic impetus for people to increase the amount of general purpose compute power in the world. If there is a law, that's the kind of law. And so there's enormous pressure to answer your question, should we continue in silicon investment? Absolutely, hell yes, to continue in it. Now, the question is how? If the number of transistors is not doubling every year, it's actually slowed down quite significantly, and it's likely that probably 5, maybe 3 nanometers are going to be the last CMOS technology. As far as I know, there's not any other magical technology. Quantum.
Quantum, yeah.
People
Magical.
talk about it.
It's definitely magical.
What year? Name a year for quantum computing. Come on, John.
We'll come
Name
back.
a year for
But-
quantum
but-
computing.
For what problem? For simulating a
Moore's
quantum
law.
system right now, for doing let's say, name the year for doing factoring
Prime
to break
factoring
RSA.
works.
Prime factoring of RSA.
Yes.
Anybody want to bet less than 20 years? No takers. See?
Right.
So,
That's the way you phrased
Well-
it. They'd feel silly if they raised their hand.
no, they're bold. They're bold.
Okay, so finish.
I'd say
Pradeep. That's
maybe
good.
15
No, you're
years.
on it, Pradeep. That's
Okay,
good.
so there's absolutely an impetus to keep improving performance. Now, if the performance won't naturally improve because the number of transistors is increasing and the clock speed is increasing, you've got to find another way. Well, the only other way I can think of is to either increase the number of devices, which is happening anyway, but there's one other thing you can do. You can actually look at important workloads and build engines that are specialized to handling those workloads. That's already happening.
Right, and
With
we're going to
GP
talk about specialized, but you're saying you get the performance for that specialized workload that you wouldn't have gotten from a general purpose
Exactly.
with
And
Moore's law.
so if there is a renaissance in silicon, it is the reemergence of specialized architectures for particular workloads.
And as the
You know-
fungible guy, you believe that a lot, right?
Well, I absolutely believe in that.
We all do.
But I think
Rodrigo, I hope you're in that game too.
I think it's pretty obvious by now that that is already happening.
The alternative is grim.
The alternative.
The
Okay,
alternative is very grim.
so I'm gonna. That was good. Oh, Rodrigo, do you want to make a comment
talk
on
about
Moore's
the
law? Dead
second
or
half
alive? Dead or alive?
Alive-ish.
Alive-ish. It's
Oh,
on.
here's why I say that. No, here's why I say that. So I do think that so we spent the last 15 years designing Spark processors and thinking about this and building large chips. And here's what I think about transistors, right? Whether that's whether Moore's law is working or not, we're trying to help by redefining what's a transistor, right? So we're just calling something a transistor. What used to be a particular structure, we We have the many things to call, well, now this thing is also a transistor, and you can pack many transistors, right?
It's
And
7 nanometers, no, it's
but
5, no, it's
here's
4.
what I think we do need. I think there is a resurgence of semiconductor technology helping the world with a variety of things. But what we struggled with for years and years and years isn't how many transistors are available to me. I think if you actually find a way to actually get me more metal, right?
Connectivity is a big deal.
We found a way to actually build a lot of dense pockets of transistors to do certain things, but I couldn't get to it.
Yep,
I couldn't get data to it. I couldn't get it out of there. And so you have the variety of issues. People talk about thermal on the chip level. We're talking about thermal at a local level on a die, right? So now you're thinking, you're thinking about the entire chip because this part is hot, but everywhere else is cold, right? So I think those are the types of things I'd say, if you can find a solution for metals and on-die connectivity, I think that will open up a
so
variety
advancement
of
will continue, just not the transistor. It's a very
And
good
there's
point.
one other thing that is really important to point
And
out.
then we're
which
going to
is,
go to the second question.
Yeah, it's really important to point out that if you look at the increase in the performance of a chip, it increases linearly with, the best it can do is increase linearly with the number of transistors. But if you look at the I/O bandwidth coming out of the chip, it actually goes to the square root. And this means that if I build the chip too large, I'm going to have memory exhaust. That problem needs to be solved actually before anything else. And we don't have a good solution to that right now.
Good point. Great points. Really good. Okay, so we're going to switch gears here. Not switch gears, but just go to the next question, which is the consolidation of silicon manufacturing, so the foundries. There's been an incredible consolidation of the market. We know it's extremely, extremely expensive to build silicon products, and the mass sets alone are tens and tens of millions of dollars. And so you got TSMC and Samsung left, really. Global Foundries is kind of out of the game. They're not investing anymore. They're going to milk the tail. TSMC, as we all know, is in Taiwan. And so if you're in this room, you've got to be thinking about China and the threat to Taiwan, a la Hong Kong, and what will happen when China makes its drive towards Taiwan. What will happen to TSMC, our leading foundry for silicon? So what is the way out of this pickle?
The US government needs industrial policy.
What's that?
The US government needs an industrial policy, and it doesn't have one.
Have you talked to Trump lately? Oh, you tweeted him just now? Yeah, okay. No, I agree, right? We've got a government that's not making it any easier, but you got to admit, if you're not worried about China taking over Taiwan, I mean, I think 5 years from now, or actually, when is that going to happen? So quantum computing is 20 years out. When is China going to take over Taiwan?
Boy.
Huh? What is it, Navin? You know the answer. Navin, just say it.
Navin knows the answer.
Navin knows the answer. Just say it. Just say it.
He's reluctant to say.
Okay, so but what are we going to do?
The same time that North Korea is going to take over South Korea, so we lose all the...
Exactly, we're left with Samsung in Korea, which isn't a lot more comforting.
They're actually a lot closer, right? They don't have an ocean between North Korea and
Okay,
South
so
Korea.
now we've decided we are absolutely screwed. How are we going to get out of this? Come on, you guys.
Well, maybe I'll jump into the fire here.
Yeah, please, Rodrigo. Yeah.
Well, I don't know how, when that all is going to happen, but I do think that if you look at the value chain of actually building semiconductors, it's way beyond the foundry, right? If you think about the foundry, you got equipment, you got tools. I mean, that entire value chain is something that's existed for many, many years, and to build up technology stack individually for whether that's China or Korea or the U.S., I think that there's just a lot of work that has to happen over a long period of time. So I don't know that we're going to see a scenario where suddenly things are closed off and there's no more business to do, right? Because in any environment, you got all this technologies that has to be built up for the value chain. Over time, I don't know. I think you're going to see people finding other ways to transition beyond that.
So what are you going to do if tomorrow TSMC and Samsung are off limits for Samba Nova? Where are you going to fab?
Where are you going to go? You can't go to Global Foundries unless you want it to, unless
Intel.
you really want it to be more like dead.
That's the problem.
That is the problem, right? It's a big problem.
So I think Lip-Bu, you should build a new silicon foundry, or somebody's got to. Someone's got to step up. Someone's got to step up and build a U.S.-based foundry, or we get TSMC to re-domicile.
Diane, it's not just a foundry problem. If you look at the proportion of electronics sold in the US and worldwide that is manufactured in Taiwan, I would bet it's a significant fraction, above 50%, way more. I'm now talking about board design, system design, et cetera.
Oh, okay. Okay. All electronics, not.
And so it's a dual problem. It's not just
Yeah,
fabs.
Yeah.
Probably right.
Okay, so nobody's going to volunteer to solve this? Navin, come on, what are you going to do?
I can't do much on that, right? Because the amount of investment required, I think this is a national thing. I think it's at the level of the US government, Indian government, and it's hard, right? Like for people sitting in this room to go think about funding a foundry, right? Because it's not only about the capital, it is also about the IP that comes with it, right? Like, I think it's a great opportunity for Samsung, for example, to step up, right? Like basically if TSMC
They're a
goes
viable
away,
competitor, absolutely a viable competitor.
but I think TSMC has done a bang-up job in building a network of IP. They've done a great job of working with Cadence, with Avago. They've done a great job of working with SerDes and IPs where when I go to them, I don't just use them for manufacturing, right? I get a whole set of things. So I think this is either a national problem or I think there are many people from Samsung in the room. They should be feeling good for the free advertisement. None of us.
Well, I do think TSMC would be smart to redomicile into the U.S. Just get out.
Absolutely.
Yeah.
Well,
do
or
the
at least-
Hopcan Broadcom play. Get out.
There
yeah.
you go.
No?
It's hard to do. It's hard to do.
Okay, so since you guys didn't solve that one, here's another one.
We tried to, but we didn't make you
I
happy.
know. Well,
I thought
I
Intel was
know.
going to fix it,
C++.
Diane.
Hey, if I was there, then we'd be talking about that. So, okay. So now that we're kind of on the path of China, so everybody, you got to think about China in the context of how it can impact U.S.-based tech companies' total business, right? China's been talking forever about the 5-year plan that they're going to become technology independent and they're going to be net exporters of technology. So again, how many years until that happens? We'll do that quiz again, but it's inevitable. So what happens to U.S. tech companies when, I mean, what are you worried about, Pradeep, Fungible, and Samba Nova, and I mean, you got businesses in China.
So I'll tell you what I see.
Yeah.
Companies in China are actually very hungry to learn, and they are much more accepting of new technology compared to leading companies, which I think are making money hand over fist and actually can afford to be somewhat inefficient. And they will want to develop almost everything internally. So this is going to allow China to catch up, I think.
And then,
Because
and then how does it impact a company
And what do
like
you think happens to your technology
yeah.
when you ship it over there to?
To the extent that we can protect it, we will.
But you probably can't.
In silicon, you can. It's easier. It's
Just
easier.
wait till you sign that deal and you
I was
have
going
to
to say,
send the IP
all those
over as
joint
part of the
venture
deal.
deals with the China
So
government will be really
it's
secure.
it's a double-edged sword, if there ever was a double-edged sword. I understand that.
I
Okay,
think
what are you
it's
going
a-
to do, Navin?
I think it's a big problem, right? Like we have companies from the US which sell into China, and then we have Chinese companies which sell into the US. Both sides are getting impacted.
Correct.
But if I look at your question, right, like China is the biggest market when it comes to broadband users, when it comes to mobile, and usually innovation happens when you're close to a market. And the US companies and Samsungs and global companies have benefited in the last decade from the boom that has happened there. And we are already seeing that Chinese companies, whether it's the telecom companies, whether it's the Huawei's of the world, or whether it is, they're buying from local suppliers. So I think maybe it's time for you and me to invest in China too.
There's high five. We got something out of this panel.
Kind of
Good.
fun. I
Okay.
can see it now.
Rodrigo, do you have are you worried about Samba Nova? You go to launch and all of a sudden the China market's like, no, we're not taking your silicon, we got our own. 25%. When I ran Intel's data center business, 25% of my revenue by consumption was China. 25%. You don't just want 25% to go away. So are you worried?
Yeah, well, it's tricky I mean, we're in a space where I think there's a lot of attention right now as far as, you know, what we do to technology, so we pay very close attention to how people smarter than us are trying to figure out how to draw the lines, right? It's, I mean, today we're not building a company that is trying to feed one country or another, right? But I think the reality of the world is this is an area where there is some national security concerns by our government, and as a company, yeah, we're paying close attention to it. It's not a simple. I don't think I can solve this on stage.
You want
tonight,
Trump again? Second time we need Trump.
So just,
Scary.
just one other thing. I would take a hard line on intellectual property because I don't think that the
Well,
U.S. can
it's-
compromise.
Okay,
it.
we're going to have to
Trying to
move
do
more
that.
quickly to new. We'll give
But-
John the next. Oops.
Yeah,
We'll give John the next.
you know what I
you
think?
Get the next
Look,
question.
China is the ultimate conundrum.
It is.
A large market that U.S. companies need access to, together with what will become a major technical competitor. And we've never faced that. And this is not a redo of the semiconductor wars with Japan in the 80s. This is a country that's got scale, got talent, got an entrepreneurial zeal. It's going to be a real run for the money, I suspect.
A real battle. Okay, now we got to get to something that's happy, right? I mean, this is like such a downer so far. Okay, so one thing back to, I think, Pradeep, what you started talking about is we have all seen a massive number of startups emerge that are developing silicon products targeted at a given workload, so application-specific compute. Now, Samba Nova, obviously, Rodrigo's one, Fungible, Pradeep is another, you have Ampere, you have GraphCore, you have Habana, Cerebrus, I mean, the list goes on, and then you have the proprietary solutions like Google and their own TPUs. So, the second part of that is they're building on some RISC architecture. And we have all seen a zillion RISC architectures in our time, from Spark, as you were talking about, PowerPC PA RISC, remember that? Itanium, the one that Rodrigo and I are trying to forget.
Don't pull me into this.
I am. You were there, I saw you. ARC, right? There was ARC, there's MIPS, obviously John, and then ARM. And now we have RISC-V. So when I look at that, I see there's two risks. One of them is you're developing a product, a silicon product, targeted at a specific workload. So how do you think about your TAM? And then that workload, if it's AI, it's evolving at a very rapid pace. So how do you then develop against a workload? You got a 3-year silicon development time, and the algorithm is moving before you can get silicon out the door. So that's risk number one. So Rodrigo and Pradeep, if you can talk to that. And then risk number two, John, is we're also, in these developments, you're dependent upon a RISC architecture actually living and surviving and breathing. I have to say, you are extremely successful with MIPS. This is the 35th year of MIPS processing. Woohoo! Congratulations.
Yeah.
So you have to tell us then, so what does make a RISC processor live on and what causes them to fail? But first start with how you think about your TAM.
Well, before thinking about our TAM, because the TAM is actually very large, it's a $120 billion infrastructure market for data centers of all sizes, edge, medium size, and very large scale ones. But in terms of addressing the risk, the way we've thought about it is pretty straightforward. Is to think about the notion of programmability in a much broader way than writing instructions for an instruction set processor. That is one way of programming things, okay? It's not the only way. And the art of building microprocessors, the smartest people in the world have actually worked on that problem. I don't think we can push it much further than it has been pushed. But there are many other ways to make things programmable, and this is what we've done. So it's a blending of general purpose CPUs with accelerators and with other programmable logic, not FPGAs, but things that are configurable. This is where silicon architecture really comes into its fore. So for the particular problem we're solving, which is data-centric computing and building a true fabric, you can actually really take that idea to town. This is what we've done. This is how we prevent, we know that applications are going to change. Their requirements are going to change. So you have to make things programmable, but you have to take a broader view of programmability.
Very smart. Thanks.
Yeah, I mean, I agree with a lot of what Pradeep said. I think we're at a point, especially with AI. I was talking to somebody the other day where they said, hey, we've been looking at this model that Google just released from May, and somebody looked at me and said, well, why are you using such an old model? I mean, this is May of 2019, right? And so if you think about how fast this world is moving, and we're designing chips that take 2 years to design, and it's tough. And so I do think we haven't disclosed exactly, kind of all the details of an ISA, but having spent 25 years building high-performance processors with an ISA, there's something really nice about that, right? Because you can create an ecosystem where people can write software, develop software, and trust that the next chip that comes out will run. right? And so where today is, I think the world's still settling into, for AI, at least for AI workloads, we're still settling into what that's going to look like. I think the different ideas of what you can do. And here's the issue that I see, though. Many solutions have decided that some application that exists today should effectively be the virtual ISA. So I'm going to create an ASIC that runs ResNet 50 really fast. Well, no one cares about that.
Very
right?
limiting.
So what we struggle with at SambaNova is really trying to figure out, well, how do I create a platform that allows you to write the stuff that you haven't written yet, to invent the things that you haven't invented yet, because if you do that, that's going to open up a lot more opportunities than just taking something small and then running it really fast. And so that's the challenge for this space, right? It's, I do think 10 years down the line, things will settle, right? And you can do a lot more of that. But today, I think it's just changing too fast. And so have to think of a different paradigm so that people can write and code without worrying about the hardware being rendered useless.
Very smart. Okay. How did MIPS survive 35 years? What was the magic? What is the magic?
Keeping thin, keeping the architecture simple and small and compact. And I think that makes sense for the core processor, but in this world where we have heterogeneous computing and accelerators, the accelerator can't do that. It can't take advantage. So the core processor can be a nice little RISC processor. That's easy, no problem. And it probably doesn't matter that much which one you pick. They're close enough. The problem is the accelerator and how to do that accelerator. And it's an interesting time because I think in some ways the industry is shifting in direction. If you think about what happened in the computer industry, we used to be vertically organized. IBM did everything from the high-level software down to the silicon, right? Then we went horizontal. Microsoft, Intel, you know, and all the providers were above that. Given the software determines the world now, it's software that drives everything. It's a re-verticalization here that's coming, and that's changing how you think about computing and how these pieces fit together. And I think it's a renaissance, as Navin said. It's a rethinking of how we think about architecture and silicon and its role in the world.
Yeah.
So Dan, there's one other aspect which is really important to point out, which is that I don't think anybody on the panel will disagree that we are in a world of scale out. And in a world of scale out, in a data center, one problem which is stable, which is not solved properly, is how do you build the backplane of the entire data center? It's what I call the fabric problem. That problem can be solved with very, very specific silicon. It does not need programmability. And that's a first-class unsolved problem today that we're working on.
Yeah, there's some fundamental infrastructure bottlenecks that can be solved without worry of rapid change. Okay, so next, Navin. We're going to talk about the investments in silicon, VC investments in silicon. So VC investments in silicon startups or semiconductor startups was at its peak at $10 billion, total VC investment in the late 90s. It then dropped to $2 billion in the late 2000s, and now over the last decade has slowly eked up to $3 billion. And I think we have Lip-Bu Tan for saving that bottom at $2 billion. He's the man that has always been committed to silicon despite all the fashion changes. And you, John was saying, you spoke in your recent blog on the Renaissance of Silicon, and you said, I commend the entrepreneurs who are putting the silicon back in Silicon Valley. And silicon did leave Silicon Valley. There is no silicon manufacturing in Silicon Valley, and so that is actually a true statement. So, Navin, then how do you look forward? So 10 billion to 2 billion to 3. When you look forward, we can't have all the renaissance of silicon without somebody putting up the money to drive that investment. So what's going to happen to the VC world around semis?
I think it's only going to go up. And the main reason is there is this myth that silicon and companies are capital inefficient. They actually aren't. To build a software company to an IPO is taking $200 to $300 million, right? You can build a product with $5-7 million. After 2.5 years, you go out with 1 million in revenue, then you triple to 3, then you go to 10, then you go to 30, then you go to 90.
Is Rodrigo's plan? Yeah.
No, he's not a software.
No, he's not a software company.
Oh, on the software side, I see.
Right? Similarly, if you look at a consumer company, right? Like you go like hey, what did it take for Uber, Lyft, Facebook to go public? You can't even remember. It's more than 3 billion. The total funding that goes in here. So when you're at the rock bottom, there's only one place to go up, which is up. And then if you look at the fundamental problems that need to get solved, as the panelists have said, software is not enough. A general purpose CPU is not enough. So if you look at the world, which we talked about, whether you look at low power, 50 billion devices in IoT, whether you look at the next generation of cloud and hyperscale companies, it is inevitable that not only will VCs fund startups, but every big company which runs a cloud is building proprietary silicon. They have to.
AWS
Because
and
the
Google,
juice is out, right? Like software people say will eat the world. It's already
And they
eaten.
have the expertise.
Okay, so then
they
here's,
have the expertise,
so then here's
right?
the question.
They
We're
know
back
the
to number of
applications.
years. We're back to number of years.
Yep.
How many years until it gets back to 10 billion?
I think probably 3 to 5.
Ooh, Rodrigo,
Wow, I
get
need
into
to
that
talk
game.
I need to talk to you.
Yeah, yeah.
I think and the main reason
Next
is,
round.
right,
Wow, write that down. That,
130 billion is being invested, right, like in the venture industry.
and we're all happy. You don't have to
Yeah.
defend it. Just do it. Yeah. Okay.
Well, can I,
You got the check.
Only
Just write it.
10%,
Okay.
right?
can I add just one comment on this? Because I actually agree with what you're saying as far as kind of hardware investments actually being a good investment. And I'll say two things there. One is we are doing chips, but if I look at my payroll, boy, you got a lot of software people there. So the
Yeah, of
extent that
course.
hardware is not enough, I
course.
think
It's
you know
always
it's
true.
yeah, you need a lot of software.
Bias
I think that's one, right? And then
Always true.
yeah, and I think the second piece, and I know there are people in here that may be thinking about getting investors and doing their own thing on for semiconductors. Boy, find the right investor. You know, when we started, you know, we wanted steady hands, right? Semiconductor startups are tough, right? There are good days, there are bad days. You know, Lip-Bu was the first one I called. and
Every
he was-
chip is late. Every chip
Every
is late.
chip.
Chip is
And
late.
it doesn't work when it gets there.
Yeah,
You need investors with patience.
yeah, you
do,
hands,
you do.
right? Because if you get through, you know, Diane, if you get through the clouds, it's a very, very good business, and it's very, very
that's
steady
what
and
you're-
very
what you're
defensible,
making.
right? And so you just got to find the right investors, and I think that's an important part of starting a company in this space.
Yeah, people that understand the value. Nice job, Navin. Good. Okay, so so on the investing side of the house, there's been a lot of studies on U.S.-based technology startups and the success rate. And the general finding is 60% of tech startups will fail within 3 years. They'll collapse. They won't get through Series A funding. Now, coincidentally, restaurants also have a 60% failure rate of 3
Okay,
years.
good.
So
Don't
if you're
start a
just looking for options in investing, you know, just toss that one out. So not just that fact, but also the fact is only 17% of tech startups make it through all the way out to exit, 17%, whether that exit is acquisition or IPO. And the ratio between acquisition and IPO is 16 to 1. So the first question to Pradeep with Juniper and John with MIPS is, how in the world did you get so lucky to be in the 1% with a company that IPO'd and became, so what is the magic? What's the magic of Juniper and MIPS?
I can tell you about Juniper that this is all hindsight, okay? That the timing of Juniper was exquisite, and I didn't realize it at that time. Had we been 6 months earlier, the technology was not there to do a full IP stack in silicon. Had we been 6 months later, there were 6 startups already. Okay?
Wow.
Doing core routers.
The timing is everything.
Timing was everything. I felt that it was urgent, but I didn't know that it was that precise. So I guess I was just lucky to think about the idea at that time, and even more lucky to find people who walked on water to help me actually do it.
All about talent, yeah.
Yep.
Well, congratulations, huge.
Yeah, I think it is about talent. I think timing is exactly right. I think you've got to get the timing right and take advantage of the circumstances. I think the other thing is, the truth is, there were a lot fewer companies. There was less venture money. There's now 5 or 6 companies focused on exactly the same space. So inherently, the majority of them are going to fail, just by definition, right? And occasionally a market is so big. You think about Uber and Lyft. I mean, we've got 2 companies, 2 potentially successful companies coming out of that. I think they can be successful long term. They've certainly been transformative. but 2 companies in the same market space. But why? That's a gigantic market when you think about it. So there are not that many markets that are quite as big as transportation.
Yeah.
I think we live in worlds of possibilities, not probabilities, when you are starting a little company, right? If you're starting to calculate my success rate, you're probably already on the wrong track, right? So I always tell people, just give me a chance. I don't care what the number is, just give me a chance, right? And I think that's at least that blissful ignorance.
So what do you, so give you a chance, but when you think about exit strategies, do you want to go IPO or is
Don't we all want to be
acquisition
the next
fine?
Google? Don't we all want to be
Okay,
the
so you
next?
want to IPO. So mark the record.
I think, I don't want to point out how much money you already have invested compared to what Google needed to get.
Okay, Navin.
Yeah, I think my feeling is having worked with Pradeep and having heard the stories of Mayfield investing in MIPS, I think these gentlemen, right, like they wanted to just build great companies.
Yes.
And IPO was just a financing event. And that's what I've seen with the 100+ IPOs we have had. That's just a point in your journey. It's really not an exit. It's actually more headaches and more trouble.
Very well said.
It's more trouble for people who want to run public companies.
And that's what you were saying,
trouble.
Rodrigo.
Exactly.
Just give me a chance. I'm not focused on IPO.
Yeah,
Give me a chance to be
absolutely.
successful.
Yeah,
That's very well
absolutely.
said. Thank you. Okay, so I would be remiss if I didn't ask a question about diversity in technology. So as you know, 23% of the tech population are women, 6% are black, and 5% are Hispanic and Latino. And you just agreed a minute ago that talent is the #1 driver of a successful startup or any successful company. Yet 60% of the US population, the talent is underutilized by the tech industry. And you can add up the numbers. 50% of the population are women, 15% of the population are black, 20% of the US population are Hispanic and Latino. So that adds up to 60% underutilized talent. So I don't want to hear about your chief of diversity officer, all that jazz, but what do you think are fundamentally the barriers? Like why is this true?
I can give you one answer, which is that, first of all, I don't believe that inherent talent belongs to one category or another category. Skin color, sex, whatever.
So far, right.
However, high tech relies on science and technology, particularly science. And scientific knowledge, particularly mathematics, is cumulative. If you don't, once you fall off the train, you're never going to get back on it. So early education in science is extraordinarily important. It also happens to be difficult. Okay? It was difficult for me. For most people, it's difficult. For some people, mathematics comes very easily. For me, it came with a little bit of difficulty, but you have to persist. Most people don't want to work hard. So I don't know a good solution to that problem.
Are you saying
Wait
that
a minute,
majority
women
of
don't want to
blacks
work
and
hard?
Hispanics
That's what
don't
it
wanna
sounds
work hard?
like you're saying.
Oh.
That is not what I said.
I'm trying to help you here, Pradeep.
Wind that
You're
back.
digging a deep hole, you know?
Take two.
Take two.
Okay, so
My point is that this problem can only be addressed by focusing on early education and making sure that people have good science education, that there are good programs in, starting from middle school onwards. That's the place to focus. Asking the question once somebody's already had their formation and they're 20, 25 years old, you cannot fix the problem then. It's too late.
That part I agree.
That's
That
the
part I
point.
agree. You got to keep the girls and the minorities in math and science in the primary education.
that's it.
Completely agree with that.
That's the main
We'll ignore all that other stuff. Okay.
So I think it does come down to social issues in society, role models, getting women to feel comfortable, getting them to not feel they're isolated because they're taking, and electrical engineering is much worse than computer science, and it's lagged even more. So we need to do that. My 14-month-old granddaughter just got her newest book, Rosie Revere, Engineer. That's the message.
Yay.
I think my feeling is, right, this problem will continue unless people in this room and executives and entrepreneurs make an extra effort. And each one of us, right, like has to make everybody aware that this problem exists. But what are we going to do to create that opportunity? And if we take baby steps, right, like in this direction, it'll make a difference. Just as an example, Mayfield has partnered with Microsoft and Melinda Gates to create a global female founders competition. It's only $5 million, but you know what? Thousands of women are applying to get that pre-seed funding. So I think if each of us, now that's a small percentage of what Mayfield invests, but you know what? It's a step in the right direction. And I think that's what people have to do. If we believe in this, I think we have to do something about it. So in each one, if we contribute 1%, 2% of our focus and say, let's make a difference, it'll happen.
Yeah, it's not the talk, it's the walk. Yep.
Underline one
Rodrigo
other
is going to
thing
say
that,
something too. Can Rodrigo go and then you go?
Sure, of course.
Rodrigo, you were going to say something.
No, I agree with all those things. My view was a little more tactical. We think about kind of, some of this is my experience with Oracle Sun, and some of it is with SambaNova. But what I noticed was, in the pace of work, and we're trying to move quickly. Sometimes we fall into habits of just kind of seeing who do we connect with. And I think those connections sometimes, if we don't take the time to really look at it, it may be more, hey, who works like me, who thinks like me? That's what it is. And so one of the things that we try to be a lot more careful about is just thinking about the result, right? What is the question you're asking? Instead of connecting on the how did they go about it? What was the end result? And we found actually a material difference in the interview results when we were doing this at Oracle Sun, where we just took the time and say, look, it's not about speed of interview. Can you actually bring people in a couple more times? Because if you actually get a breadth, you may actually find that there are people that think differently that actually can get to some pretty creative answers if you give it a little more time.
That's well said. Thank you for that. And you have impressive results of your own executive team.
Yeah, I mean, we're small. We're a small company right now. We're 36% of the executive team is female today, and I mean, a lot of these are long-term relationships. I know we've got a couple people here. I know Penny's here, but I mean, these are relationships that you build over a long period of time. And Penny's been with, Penny, I've worked with her for 20 years, and she's taped out every chip we've done for the last 12 years. And so I mean, these are relationships you build over time. But I do think it's something that I think you have to make an effort to cultivate those relationships.
That was well said. So thank you for all of your answers. Oh, you were going to add something?
I just want to add one other thing, that when you're trying to solve hard problems, it's really important to have diversity of thought. And if you try to hire people like yourself, you're not going to get that.
Yeah. Well, I'll say what I always say. We need you gentlemen, because you can't ask the marginalized population to solve the marginalization of the same population. It doesn't work. You need the majority population if there's going to be any change. So we need you guys. Okay. Okay, I feel better. I got that off my chest.
Okay,
so,
good.
As a big wild one that we're going to really put you on the spot, you got to come up with something really insightful, John. Ready? Okay, so what is the next AI, right? We had business intelligence, structured data. Then we had big data, Hadoop. Everyone ran out and got a Hadoop deployment. Then we had machine learning, traditional machine learning. Then deep learning and reasoning systems. Okay, so what's next? How does that evolution continue? Where do you see AI going?
The AI is going to go to AGI, to artificial general intelligence. I think it's going to be a hard process to get there, but I think you're going to see machines which satisfy the most stringent version of the Turing test you could ever imagine. And, there are probably more than 10, but probably less than 30 or 40 years away. And the rate at which, so there's one thing that's going as fast as Moore's Law, and that's the rate of progress in machine learning.
Amen.
It is going as fast.
Moving.
The number of papers, the number of people.
VC investments.
I mean, you look at the undergraduates at Stanford, not only is computer science the largest major, but the largest fraction of the students want to do ML stuff. They want to do AI, right? Yeah. So I think there's an injection of talent that is really phenomenal, and I think it will push the technology very fast.
Yeah, that's well said. Anyone else want to chime in on what's
Sure.
next?
So I think it's artificial general intelligence, but there'll be a particular form of it, which is federated learning. Because the only way to scale is to actually learn at many places and then combine the results of that learning effectively. And now when you have this set of weights, it's now the sort of boiled down, digested learning that you've done, and you can distribute it like software everywhere. So concentrated learning and then distributed learning, but then inference everywhere. So that's the model I think we're headed towards.
Yeah, Yeah, I'd add to that. I mean, I always talk to the team about the fact that with AI, we talk about AI like it's one thing. AI is like the internet, right? It's like what's going to happen. We do think that we're in the very, very early stages of AI. If I think about the world, it's about connecting people, places, and things, right? And you think about kind of what everyone's doing is very statistical in nature. I mean, today we take very precise Intel processors, right, that can do a number of significant digits, and we calculate everything down to that. But the reality is there's a lot that you can actually do with a statistical-based calculation that's actually very useful. And so if you take the world that's just full of data, most of which no one cares about, right? Most of the data, and you actually try to extract what's useful data, and then you try to connect people, places, and things. It's a hard problem. It's a very hard. Just getting to the right data is a hard problem, right? Let alone connecting them. And so I mean that's a problem that I think we're going to be trying to solve for the next 10, 15 years. It's not a trivial thing to wrap our brains around.
Fun, tough problem. Yeah. Any ads?
I think the only thing I would add is I've seen so many of these investments, but yet finding something which is going to bring intelligence at the edge, these 50 billion devices which are connected to the internet. I think eventually all this stuff needs to move there. And it needs to be simple. It needs to be easy because bandwidth is a huge issue. You're not going to move data from these things all the way up, right? You need to solve the problem there.
Yeah, distributed compute at the edge. Yep, what Pradeep was talking about. Yeah, take a lot of bandwidth.
Yeah. This is like doing inference and processing at the edge.
Analytics at the edge. Okay, so that was my last question. So someone now has got to stand up and ask a question. And we do have a runner on it's going to take longer for the runner to find the person asking the question than it is to ask the question. Why don't you say it and I'll repeat it? State it and I'll repeat it. What's your question?
Loud voice.
Or come stand up on stage. Just come on.
Okay. It better be a good question.
Yeah, it better. Here you go.
That's right.
What's your question?
Okay, so I'm a big believer of application-specific computing, right? And this is the only way probably to solve the post-Moore's law era problem. And we know that one critical thing is the accelerators. Now the question is, where does this accelerator go? If you look at the server,
it's going to be a short question.
Data center or edge, right?
Okay.
You have two socket CPU and a bunch of SSDs, and then you have a network card. So where does this go? In the Google, it goes to the GPU, TPU, and then Mellanox goes to the network card called SmartNIC. And Pradeep, you're putting something on between the network and the data storage. So my question is, where's the ideal location? One thing I observed is...
Okay, that's the question.
All right.
Okay.
You're not actually on the panel. Okay, there you go. Okay.
The answer is it goes both.
You want me to repeat the question,
It obviously
Rory?
goes both, right? It goes both.
The answer is it depends.
You're going to have something at the edge that does some inference, right? You're not going to try and do learning and training at the edge. You're going to do that back in the data center. And you got the data center to back up, right? So you speak to the phone and it tries to do speech recognition and then concludes it needs some help from the cloud, maybe sometimes, rarely, but it may. That's what'll happen.
Yep. Agreed.
Okay. Anyone else want to add to that? Everybody happy? Okay. Next question. Gentleman in front, you want to come up on stage?
Here comes the mic. Here comes the mic.
There you go.
So my question is on the comments you made about AI, and specifically, what do you guys think, first of all, do you think that there needs to be better programming interfaces for neural networks and for AI in general to be like adopted by, you know, different industry verticals so that like normal people can, you know, like do AI in their own business environment? So that's the first. And a follow-up to that, like how important do you think it is for, you know, something like a Microsoft Paint for AI, whereby the compute and the network are able to speak to each other in a visual way so that, again, normal people are able to like actually use this? And I asked this because my company was sort of acquired by an asset manager, and right now the biggest challenge for us is actually finding AI talent other than me, which is like you can't just run an entire AI department.
So that
with
is
one
really,
person.
that's a good
Normal
question.
people don't code normally, right? I mean, there's just writing code already puts you in a small minority of people. Writing AI code puts you in an even smaller minority. We're expanding that group as fast as we can, and there are lots of attempts to educate more people about ML in particular, but it's going to take time. The application space is racing much faster than our ability to produce people.
But his point is well taken, because you have global Fortune 500 companies. They all have IT organizations. They're all trying to deploy a AI solution for their corporation to help top line and bottom line, and they don't know how to do it, and it's too complex. So I mean, it is a real problem. So
No, I mean, look, there are a couple of levels already. This is why I think this is kind of early days for AI, right? And I've told Lip and other people this. I wouldn't have never done this company if somebody like Google didn't come in at least with a framework. We're already ahead of the game with TensorFlow. Right? I mean, I came from a world where we had to recompile programs for every single person, right? And that's a very, very difficult world. I mean, this is why Intel wins, right? Because you've already got the market share. But with TensorFlow, I think we're way ahead.
So you're betting on TensorFlow as the
TensorFlow's
platform
a
that'll
start.
win in the future.
It's a start, right? I think if you really think about how many people can even code at that level, that's a minority, right? And so I think what you're seeing is both ends, going down and going up. You're starting to see people build infrastructure to allow the masses to do it, because it is going to be very difficult for you to say, okay, well, we can all pay $1 million for data scientists to come in and actually write, these.
That's where Accenture comes in and all
And I
this
think
stuff.
taking a end-to-end perspective, right? This panel was on silicon hardware. I think there's a lot of innovation which is happening in the low-code, no-code movement, and there's a bunch of companies who haven't succeeded, but are trying to solve this problem, that how all these ML algorithms, all these algorithms, they can be provided as a service, so that any normal person can start using this, and frameworks like TensorFlow and other things help. So it's a great area, right? Think payments, I just called Stripe. I need voice, I just call Twilio. So eventually all these models have to become as easy to consume, and all the complexity has to be hidden. So I think that's your next startup opportunity. That's what will happen.
And I think it'll happen, especially if you constrain the domain to be
agreed.
domain specific.
Agreed.
Trying to solve this problem generally is much harder.
And there is a lot of VC investment in startups in this space.
Yep.
Okay, next question. Oh, gentleman back.
So, given the shortage of experts, and given a set of human-specified goals, how many years do you think it's going to take for computers to start programming themselves?
Well, computers are already kind of sort of programming themselves. I mean, if you look at these, GANs, they do exactly that. For in a very specific domain again. Okay.
What does programming mean? That's the other question, right? I mean, you look at so many of the applications today. Most of the work today is just in getting your data ready, right? And cleaning and labeling your data. There's a lot of work just getting the data sets correct if you want to train a model, right? If you're calling training the writing the program, right? But there's a lot of work just going into trying to curate that data set so you're training for the right thing. And so I actually see the world moving there first, that you're going to see the traditional computer scientist that was decomposing the program and writing little procedures to do X, Y, and Z. You're going to first move over to a bunch of people that are experts in actually curating the data, making sure that you got the right data so then the machine can train. How long before a machine can just do that part of it? I don't know, right? But that's a hard problem. It's a hard problem.
Yeah, but that's probably the key insight, I think. Look at the natural language translator that Google had before they switched to the ML-based translator. It was 500,000 lines of code. The new version that's ML-based, that's all trained, all on data, is 5,000 lines of code. So in some sense, the 495,000 lines of code that disappeared were written by computer, because they were written by training a neural network how to do that. And maybe that's the right way to look at it. There'll still be a human piece, but it'll be written in some automated fashion that doesn't involve people writing lines of code.
Well, and then the labeling problem, you can somehow convince people to do it just during their normal course of business. For example, translation.
Yep, ImageNet.
ImageNet, for example.
ImageNet, yeah, exactly.
There's a cat, there's not a cat, etc.
With the advances in AI, right, like full programmability hasn't happened, But what is happening is, like you do autocomplete on Google, when I do a search, there are tools coming out where when developer is writing code, the next library suggestions start coming from the machine itself, right? So we are moving into this autopilot, not fully autonomous world. And it will happen, right? Fully autonomous, I don't know when it happens for programming, but this autopilot thing and suggestions are like beginning to happen as people write code.
I agree. Good comments. Rory?
Okay. So at the very beginning, actually, I heard Dennard scaling is ended about 10 years ago, and that's you're fighting gravity. And silicon CMOS scaling and cost, that scaling is ended, you're fighting gravity. And then the answer is application specific, go up the stack, make yourself more efficient, but the inherent silicon you're building on is declining, deteriorating.
You're absolutely
I'm
right.
exaggerating a little bit, but
No, you're absolutely right.
So where's the innovation at the silicon technology layer?
Well, that's what Rodrigo said. We got to work on the metal layers, right? So don't worry about the transistor links so much. Fix the metal
My
layers.
local view of it.
Yeah, that's only a small part of the problem. I mean, I think you have to accept that there are some fundamental limits that you're hitting, right? I mean, it costs a lot more to communicate data across a chip than it costs to do a simple recomputation, right? So you've got to accept that there are some real hard limits. And really the move to domain specific is really about, well, now efficiency matters a lot. It didn't matter before. Moore's law is going to the moon, right? You didn't need to worry about tuning up efficiency because the next year you were going to get twice as many transistors.
But John, isn't it still on the same base silicon?
No, but that I think that's a brilliant point because how do you compensate for the slowdown in Moore's law? You make sure that those transistors you're using are much more efficient in getting the workload that you need done. So that's why we get all these application-specific solutions.
That's
so
exactly
you're
right, Diane.
compensating for,
That's exactly right.
for Moore's law. That was good. We're back at the beginning now. Did you know Moore's law is dead?
Well, it's there's Noyce's law, right? Noyce's law. The cost of the fab goes up as the square of the decrease in line size. I mean, that's a driver too.
Okay,
because it means the transistors get more expensive.
Okay, so we still got time for questions. So there's a bunch of hands up. Oh, it's hard to see you. Go ahead.
Yeah. All right. So in the late 70s, early 80s, the processor war picked up, and Intel became the ultimate winner with Motorola getting out, right? So similarly, how long is it going to take for the AI processor war?
That's a good question.
I don't think there's going to be one. Well, there is already one winner. It's called NVIDIA, but there's many competitors coming.
Actually, that's a very good point. You can't ignore that there is a pretty sound incumbent. Yeah.
And by the way, the one thing that NVIDIA did very early was to come up with CUDA, and that's bulk of why they're ahead.
It's all about the ecosystem. Back to talking about it, how does a RISC architecture survive when you have a sufficient ecosystem around it?
You need the language.
You need the language because I think in these generations of machines that are domain specific, they are not going to be binary compatible. It's not going to be the model we used to have, right? That it's not the same. It can't be because otherwise you can't do enough innovation. So,
Too hard.
So you're going to have to think about a higher level of compatibility in terms of moving software forward.
Exactly right.
I don't think we have figured out where the battle lines really are, right? I think we're thinking AI is a very broad thing. I think over the next few years, I think there are going to be specific use cases which will start delineating kind of what are the competitors within these spaces. And
well, just watch the way the space works out between people going into after inference and edge markets versus training markets. They are completely different spaces.
That's already happened.
It's already happening.
But, I do have an opinion on the GPU, and I think Rodrigo SambaNova has a big opportunity because even if you talk about NVIDIA, it was a graphics processor that then moved to a high-performance computing scientific compute that then opportunistically fell into the deep learning space.
Yeah, they had some pretty good ideas.
It is not an application-specific compute engine for deep learning, and it is not optimal, which is what opens up the door for all these startups.
It's not bad.
It's expensive too. You should.
It is
have you
expensive.
bought one lately? Yeah.
No, it is expensive. Well, guess why Google decided they need to do their own silicon.
Exactly. Wait, do we have a mic for someone?
Yes.
Hi.
Hey, we need diversity in questions.
Diversity in questions. Okay.
Just saying.
So, we talked a lot about the move to application-specific semiconductors, and as startups go and address that. These are not like the giants like Intel, Broadcom, Qualcomm, etc. So what you're going to have is, in those startups, you're going to have a duplication of your CAD teams, your tape-out teams. You've got your ability to go do some negotiation with the two only foundries that are left. You're going to fight for ML algo talent, as the gentleman there said. So how are we going to get, ROI or basically more efficiency in those startups when there is a lot more of these as opposed to a smaller?
So I think the question is.
I kind of got lost on that.
The question, how do you get, as a small company, how do you get compete against the folks with economies of scale?
Yeah, as SambaNova and Fungible, you won't have the scale as, let's say, a Marvell or a Qualcomm, etc. When it comes.
Well, okay, I lived it, right? So, when I was building products for Sun, people actually return my calls, right? And when you're SambaNova, no one pays attention to you, right? But it's a reality, right? It's a reality, but I think I'll say this. There is an entire ecosystem out there for semiconductor startups that actually you can lean into, right? And there are vendors who are actually subscribing many startups and then negotiating on their behalf, right? Correct. So I think it is important for you to realize that you don't have to fight this with the folks, the large folks, and there are a lot of partners that you can use for that. And so, I mean, we've been able to take advantage of that. It's been great, and so as you grow, you have to worry about the transition. How do I go from, growing out of this ecosystem that is target for small startups to then starting to negotiate this yourself where your, negotiation leverage is not as strong yet. But I think early on, there are other ways you can do it.
So there is one thing that startups have going for them, which is they have an idea. And if the idea is really good, it'll catch on. If the idea is not good, it's going to die. And I'm a big believer that most innovation actually happens in startups. It's hard to do innovation at scale. It really is very difficult.
So you don't believe in entrepreneurs? It's only
It's tough.
entrepreneurs. Dang. Okay. To Pradeep's point, the next question has to come from someone that's in the minority population of tech. You have to be a woman, a Hispanic, an African American, or a Native American, and then you can talk. Uh-oh.
Right here.
Oh, Diane. Okay, good.
Come on.
Yeah, it's yours.
It's yours.
Got the mic. You got the mic already.
Oh, she's a runner.
You can ask a question.
Penny? Wait, where's Penny? Penny?
Is Penny here?
Connie
she's
has
not
a
here?
question.
Oh, she's right there. Penny's over here.
You have a question?
There
Okay.
you go.
There's one.
Thank you.
A few of you mentioned a couple times briefly how bandwidth and I/O from chips is a problem. Talk about that some more. What's the solution? And how will that change things, especially now in the context of Moore's Law being over? Is the interconnect more important, less important?
Yeah,
Well,
data movement's all in your
I've been thinking about this problem for a long time. I can tell you a little bit about what I think about it. If you look at semiconductors, one thing you will notice is that growth still applies to flash memory. Okay? Ask yourself why. And the reason becomes very obvious because people can actually use the third dimension very well. Why can they do that? Because the power consumption per flash cell is very, very small. Okay? You can't do that in microprocessors and DRAMs. But if somebody could figure out how to stack those things, life would be really, really good. You'd open up that bottleneck.
Well, you
So
can
that's
stack DRAMs, you just can't stack them on top of a processor.
But that's where you need to stack.
That's where you need proximity to reduce the connectivity.
I mean, look, the boundary, the chip boundary has been there forever, right? It's been there forever, and it's always been a limitation in some sort. The challenge the architect faces is to figure out how to organize the chip and the architecture so you don't have to move as much data across that boundary. That's the way to think about the problem.
But because of that, the direction is now to go to smaller dies with high-speed packaging interconnect. So part of how we're compensating for the slowdown of Moore's Law is by inventing new packaging solutions that you can create very high-speed interconnect. So there's invention happening. It's just not a.
So Diane, that's a very interesting point. That because as you reduce the die size, you run less into the square root of area problem.
Yeah, yields go up. Yep. Costs go down?
Depends
Oh,
on what
come
you do with the
on.
on-chip silicon.
Yeah,
It depends on what you
absolutely.
do with the on-chip silicon. Because if you can get enough memory on the chip, you can break through and reorganize the way the data works.
I'm taking the gauntlet, diversity
Okay.
and questioning.
All right, good. I'm glad.
So,
Wait, here's a mic coming to you.
I think they can hear me.
Yeah. Well, the video won't pick you up.
Okay. So, John, you founded and ran MIPS in the 80s. Juniper was in the 90s. Navin founded a company in the 90s, and he's been investing in many companies since. And SambaNova is 2010s. What's different about building a company through all these decades?
That's a great question. That's
Oh,
a great
wow.
question. So, John, you have to answer. No, you're
It's
the
a hell of a lot more
veteran
complex.
on this, I
I
right?
think a lot of the things are the same. I think a lot of things are the same. There's more competition. There's more money, and hence great ideas are funded multiple times, I think to a much larger extent than they were earlier. I think many other things are the same. Look, this is still the technology capital of the world. This is where people come, and people who are willing to take risk and join an entrepreneurial team come. So I think we still have a lot of the advantages we had in earlier times. It's a lot more crowded. I mean, if we don't solve the problems of what it costs to live in the valley, we're going to kill ourselves. It's not somebody else who's going to kill the valley. It's the valley not facing up to the challenge of living here and building transit and doing all those things. We're going to kill ourselves if we don't fix the problem, and shame on us if that happens.
And there's one clear difference I see between starting Fungible and starting Juniper some 20 years before, which is that the number of rules and regulations that startups face is a lot more.
It's much harder. It's much harder to go public.
Like what? Say, get specific.
Not only
What's
public,
something
but even
that you-
before.
Well, SOX, Sarbanes-Oxley makes it a lot harder to go public.
But so specifically between Juniper and give us specific examples of Juniper and Fungible.
Well, you know, specific examples. Just the number of things you have, number of I's you have to dot and T's you have to cross is just much, much larger.
What was
The
Juniper's revenue when you went public?
Juniper's revenue, 400 million.
Yeah. So today, that's a marginal amount to take a company. Well, either you go public losing a lot of money, or you go public making.
Well, except
Good.
we were
400 million. You'd go public at 400
6
million.
million,
wouldn't you?
100 million
profit?
for. We were profitable.
400
Yeah.
million?
So
I don't remember the exact numbers. We were profitable.
So having
Really good.
having been a founder, right, like in the mid-90s, and Pradeep, you could relate to this, and even in the 80s, I think in the 80s and 90s, from what I understand, and I faced it first time when you're an engineer coming out of Stanford or any other university, the first thing a VC investor would say is you have no business experience.
Yeah, they would
you
say
get a
that.
co-founder.
Yeah, they
it's
would say
completely
that.
changed.
Yes, that is a big
Right?
change.
Like basically,
That is
a
people are
change.
willing to
Except
give.
a few companies invested in people that didn't know what the hell they were doing when it came to the business.
Which we were still doing, but I think people are always saying like, hey,
Where are your MBAs? Where are your MBAs?
yeah,
right?
Now,
Yeah,
I think
now.
like if you're a tech entrepreneur, you're being given a chance.
You're right.
Yeah.
That is
a
a
difference.
smart
Big change.
change.
I
That
don't
is
know
a
if
big
And
I
the,
can
the
think
rise
that-
of founder CEOs, that's
Yeah.
different. Founder CEOs that don't have any experience.
It's massive.
Yeah,
That's very
yeah,
different than it
very
was.
different than it
Absolutely.
yeah. Hey, what hasn't changed is diversity, though. Okay.
Slow, Diane, slow, slow,
I know,
slow.
sorry.
Yeah, she had a question.
One more. We can take non-diverse questions. We will. You go ahead, sir. I know you've been waiting a while.
Yeah, so taking a different side, now with the advent of 5G, how do you guys see that revolutionizing computing, especially at the edge?
That's a good question. We haven't talked about 5G at all.
There is a degree of hype in 5G to begin with. Just there was in 4G.
When do you think real 5G will be in full production? Pick that
Well,
number.
I think that it's
How
going to
many years?
require a lot of somebody spending money because the density, of
Billions.
cell sites
Yep,
is
that you need.
10x. So it is 10x
It's 10x.
because
Yeah, the infrastructure build out.
So that's
is
the big issue,
overwhelming
is putting up
for
all
the
those
telcos.
towers
It's-
and
it's
the
just that.
backhaul. And the backhaul.
And the backhaul.
Yeah.
And so you look at the telcos, they're not making the investment that they had once
Well, they
committed
can't
would
afford
make.
to.
They can't afford to.
So
Look
they
at
will
AT&T,
they will only make those investments in areas that have very high population density,
Yeah.
where they get a return. Yeah.
where they can get return. Otherwise,
And power is going to become a big issue.
Absolutely.
Right? Because it's already an issue with your smartphones and the
Yeah,
edge
yeah,
devices.
yeah.
And I think there will be need for innovation, like what you talked about on the interconnects.
Yeah.
There's going to be need for solutions which are the equivalent of fans, right? Like, how do you cool these devices? Because to the point you made earlier, microprocessors, right? They're throttled. They never run at full efficiency.
Right.
Yeah.
Well, by the way, speaking about industrial policy, I mean, the US is complaining about Huawei, but we have no company in the US doing 5G.
Yeah.
None.
Yeah, exactly.
Right.
There's Ericsson and there's Nokia. They're not US companies.
Right.
Wait, Huawei would be a whole other panel. Whew. Okay, it's a good question.
Question for you. So in the 1980s, Carver Mead started talking about neuromorphic computing. Fast forward 30 years, we're still talking about neuromorphic computing, but we are seeing investment in the space. I'm curious, how close do you think we are to new architectures that are inspired by the brain?
Well said.
How inspired do you mean? I mean, a DNN is inspired by the brain, right? If what you mean is, when are we going to move to analog computing models? That's a very tricky issue because the march of digital technologies continues to just stomp out attempts that periodically occur for analog.
So I would be
and I don't know. I think it's hard to say. I've yet to see the compelling killer app that's going to move us in that direction.
So John, I'd be a little bit careful about that because in inference...
I didn't say it couldn't happen.
In inference, there are approaches that you can use pieces of analog technology.
But small bit inference, I mean, you need low precision, right? Inference, low precision.
4 bits.
Throw all the bits,
That's
throw all
why
the
I'm
bits
thinking
away.
the volume, right? Yeah, low
Yeah.
precision,
Low
low compute,
precision,
but high
very low
volume.
power.
Okay,
And high
here's an
volume.
observation. All interesting applications over time have moved from analog space to the digital space and not gone back. So here's one you're predicting is going to go back somehow. Maybe, but show me. Show me.
Okay, last question. Better be a good one.
Okay,
Navrina?
right here.
Oh, wait, she's going. Navrina's go. Okay, we'll take 2 more then. Navrina, go, and then...
Awesome, thank you. So one of the things that while you were discussing the talent pipeline, I think wasn't discussed was reskilling. So one of the common trends I'm noticing in companies like Qualcomm, Intel, et cetera, of the world is people who've done really good, like let's say have 25+ year experience of building wireless modem are now building AI chipsets. But I think there's an inherent gap in the understanding of what AI really means and how it needs to be solved in these new silicon age. So would love to understand from you guys, like what has really worked well in reskilling, especially in silicon, especially because most of the talent that's going into colleges is excited about computer science, machine learning, but not excited about ECE and AI architectures.
Good question.
I guess I'll take at least a crack at that. I mean, I'll start with the fact that, as a company that's trying to hire a lot of AI folks, one of the things I noticed was everybody on LinkedIn is an AI expert, right? So I would start with that. Do not claim you're an expert if you aren't, right? I mean, it's what I'll say is in this space, there is a lot of need for the expertise that exists out there, right? I do think that the underlying premise of how we're actually going to do computing is changing because the workloads are changing. And so I think that's actually a nice level playing field for a lot of people, right? I mean, we've done a lot of work with traditional OSs and things like that, and suddenly you got these models and you're not programming anymore, you're curating data, and so there's everyone's learning, right? But my advice is, do something you're good at while you're doing that as well, right? Because in the landscape of what we're trying to do, we are applying existing skill set just into a different space, right? Not to say, hey, I'm a great SRAM designer, I'm going to go and become a new, a neural net developer, right? It's you need both of those things, but I would say that you can apply a lot of those skills still in the same space.
Great, and now the last question. Yep.
In the beginning of your talk, and actually towards the end as well, you talked a little bit about how thermals are holding back the process. And now we have some high performance processing that's necessary. And we're holding the CPUs back in order to keep the heat down. So who's investing in solving the thermal problem so you can unlock the existing CPUs that can go a lot faster without having to do a lot of this other kind of work?
I think VCs are like us.
Yeah, there are some. Remember, it's a two-sided problem. You have to get the power in and the heat
power
out.
and the heat out,
And
yeah.
you have to solve both sides of it, right? And one is a metal related to metal layers and interconnect at that level, and one's the
DC
but I think we're going to get liquid cooling back, at least in data centers.
Well, we already are.
We're already
Liquid-
there.
liquid
We're already
cooling
there,
is
right?
in most of the large
TFP3
data
is
centers
liquid
today.
cooled. I mean, we're
it's
going to
liquid
be
cooled.
there.
And
We're
I
gonna be
think the
there.
packaging technology, not back to
Yeah.
packaging, I don't know why I love packaging tonight, but packaging technology, same thing, running water through packaging technology to pull
Yep.
out the heat. So that becomes the real
We'll
key.
make some progress.
So I think we are done, and we're going to turn it back over to Karen, and we're all going to stay sitting here. Don't move, gentlemen.
Just for a moment.
Rosie. All right. Good job, Diane.
I want to thank our speakers for sharing their perspectives so candidly, and Diane for bringing that snap, crackle, and pop to the evening for all of us. Thank you so much. As a small gesture of our appreciation, we would like to present to you, the Churchill Club speaker T-shirt.
Yeah.
Please wear that in very good health.
All right.
You have been a wonderful audience. Thank you so much. Please access the YouTube video of this and share it with others if you enjoyed the program. Thank you so much. Have a great night. Good night.